We are in Unit 9, and I thought I would take a moment and review what all we're going to be doing in Unit 9. So Unit 9 covers advanced integration techniques, and we start off in the first section reviewing our known integration techniques, which are pretty much just the power rule for integrals, and also the antiderivatives that we know, like the antiderivative of cosine, the antiderivative of sine, and things like that. We also learned the integrals of functions that yield an inverse trig function. So we're going to spend a unit reviewing those, or not a unit, a section reviewing those. Then we go on to the new things. So section 1 is review. Section 2, we're going to be doing integration by parts. We'll learn all about that. Section 3, we will use partial fraction decomposition to integrate. In section 4, we will be looking at antiderivatives of powers of trig functions. And then in section 5, we will do integration using trig substitution. In section 6, so integrals, 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 integrals. Then in section 6, we are going to take a look at what's called L'Hopital's rule. And L'Hopital's rule is a way to evaluate limits. And it sounds like that would not go in this unit on integration, but we need L'Hopital's for improper integrals. So that's why L'Hopital's fits nicely there, okay? So improper integrals, we'll learn all about those, all right? So that's where we're going in Unit 9. So today, for this section, this is Notes 1, and for this section, we will be doing our review of integration techniques. So let's take a look at what we know. We already know how to integrate many, many functions. Basically, all we know is the product rule for integration. Okay? So we have to get whatever our integral looks like, we have to get it into a form where we can use the power rule. Okay? You need to know the antiderivatives for all of the trig functions, inverse trig functions, okay, and 1 over u du, so you need to know those, and that's really it, okay? So that's all we have. So we have to manipulate our function and our integral so that we can use one of those two things. It's all we have, okay? So tips though, tips. Know all of your antiderivatives and derivatives. Know all of them. I gave you guys a formula sheet on day 1, and whether or not you've been following along on it, it has a list on the second page of all of our derivatives and all of our integrals. Okay? And you really need to know these. All right? You really do need to know these. We need to be able to recognize things that we can easily take the antiderivative of. All right? You see that our integrals, we don't really have a lot of things to memorize on the integrals, and some of them are very obvious when we just think of antiderivatives. Okay? A lot of them are very, very obvious. Okay, this one here you don't know yet. We need by parts integration for that. So that's our last one that we'll be looking at tomorrow when we do by parts. Okay? Everything else though you really should know. You should be able to recognize these as their antiderivatives. Okay, so pretty much know those. Another tip, if you have an antiderivative, if you expand it, then you might be able to use the power rule. So expanding it will allow you to use a power rule. Remember that there is no product rule for integrals, only for derivatives. So we have to get it into a form where we can use the power rule. Okay? Know when you can divide. Always divide if the integrand is an improper rational function. Okay? That means that the degree of the top is greater than or equal to the degree of the bottom. Don't forget u sub. We choose a u so that we can do the power rule with our u function. Don't forget u sub. Don't forget that you can complete the square in the denominator so that you have an antiderivative of an inverse trig function. Okay? Use trig identities. Sometimes we have to use trig identities. Multiply and divide by conjugates. Okay? Add and subtract terms in the numerator so that you can use u sub and the power rule. All we have is the power rule and antiderivatives for functions that we already know. And that's it. So let's take a look at some examples. And I will tell you that the more you do, the easier it is to know what to do. So practicing is crucial here. Crucial if you want to be good at these. Practice, practice. Do all you can. All right, so in this example, it's definitely not one I can use the power rule on yet. I need to expand, so I'm going to distribute. So this would be 3x plus 2 dx. And now I can use the power rule. So now this would be 3 halves x squared plus 2x plus c. And that's it. Okay? Number 2. In number 2, again, there's no quotient rule for integrals. So we cannot just take the antiderivative of 3x and divide it by the antiderivative of x plus 4. It doesn't work that way. So what can we do? Well, here the degree, it's a fraction. So I look at the degrees. It's a fraction. The degree of the top is 1, the degree of the bottom is 1. If the degrees are equal or the top is bigger, we go off to the side and we divide. Okay? So we're going to divide. In this case, I'm going to use synthetic division because I can. I will always use synthetic division if I can. So I put the opposite of 4 in the box, and then I put my coefficients along the top. I have a 3 from the x term, and I need a 0 for the constant term. Bring down your 3, multiply, and add. And this was a very short division one, but that's what we have to do to divide. Okay? So this integral becomes, this was x, so this is just our constant now, 3, and the negative 12 is our remainder, so that's negative 12 over x plus 4 dx. Now we know the antiderivative of 3. dx is 3x. And then the antiderivative of this piece is a natural log. We know it's a natural log because the derivative of the bottom is a number. If the derivative of the bottom is a number like this, then we just get a natural log. So this is going to be negative 12 natural log absolute value x plus 4 plus c. If the derivative had been a 2, then remember we would have had to have a 1/2 out front. Okay? So that's that. Too often I see students make a mistake. A common mistake that students make on this is they do this kind of thing. And they turn this into 3x over x plus 3x over 4. That is not true. Those are not equal. Okay? This is not equal to that. You cannot split up the x and 4. You can't do it. Alright? Alright. this next problem. So in this one, we cannot go off to the side and divide, right? We have this e to the negative x, so you ask yourself, goodness, what do I do with that? So my first thought is always to do a u sub, where u is the whole bottom. And since I have this complicated bottom, you may not want to write this down quite yet, because this isn't going to work. But this is what my thought process is. If I let u be that bottom, what would du be? Du would be negative 7 e to the negative x dx. This is why we have to know how to do all of the derivatives, you guys, because of your u sub. You need to know every derivative to integrate, okay? All right, the negative 7 is not a problem. I could divide that, but I never divide by an x, right? That has to be here. Do we have an e to the negative x on top? No, we do not. So, cannot do that u sub. We have to think of something else to do. So here's my thought process. I want to do something. So I'm going to change this e to the negative x to 7 over e to the positive x. And then that gives me an idea. What if I multiplied top and bottom by e to the x? That way I would get rid of that x right here. If I do that, then I have 2e to the x divided by 7 plus 4e to the x. Now let's let u be the bottom. Du is 4e to the x dx, right? So 1/4 du is e to the x dx. I have the e to the x dx, so I can replace e to the x dx with 1/4 du. 1/4 times 2 is a half, right? So this will be 1/2 integral 1 over u du, which is 1/2 natural log absolute value of u. I'm going to go put in what u is plus c. Okay? This would be a safe stop spot. I do notice that this 7 plus 4e to the x, e to the x is always positive, which means that this argument is always positive. So I can rewrite this without the absolute values, and it makes it slightly more simple. As a multiple choice answer, you would probably see it with the parentheses. Okay? But if it's an FRQ, that's a safe stop. So you can totally just safe stop there. Okay. So, one other word about this one. This e to the x one. The problem with this was that we didn't have an e on top. We had an e on the bottom, but not on top. By multiplying by e to the x over e to the x, we got an e on top, and that was very helpful to us. Okay? So when you see a problem and there's an e to the x on the bottom, but none on top, you're going to need to multiply top and bottom by something that will get an e on top as well. Okay, number 4. All right. Whenever I see a trig function, the first thing I do is take a look and say, do I know a function whose derivative is what I'm looking at? And the answer is no. I do not know the answer, or a function whose derivative is 1 over cosine theta minus 1. Trig integrals are tricky, okay, because there's so many things we can do with them, all right? In this one, my options are kind of limited. Remember, you guys, you cannot split up this cosine theta and the 1. You cannot make it 1 over cosine theta plus 1 over negative 1. You cannot do that. That's not legal. There's no math property that says that, yes, you can do that. Okay? So, what do? Well, when I see this, I think, okay, I'm going to try to multiply top and bottom by a conjugate. Because really, I don't know what else to do with that. The conjugate of cosine theta minus 1 is cosine theta plus 1. So now our integral is cosine theta plus 1 over, let's FOIL this out. We're going to have cosine squared theta. The middle term will zero out. That's why we did the conjugate. And then minus 1 d theta. All right. What is cosine theta minus 1? Now's the time to use a trig identity. What is cosine theta minus 1? Well, sine squared theta plus cosine squared theta is 1. So cosine squared theta minus 1, be careful, that has to be a negative sine squared theta. Okay, and again, I got that from sine squared x plus cosine squared x is 1. So cosine squared x, I'm bringing the 1 over to the left. The sine squared goes to the other side, and it has to be negative. Okay? All right. Now there's a single thing in the denominator. So now I can split up the numerator, and that might be handy. So we'll have negative cosine theta over sine squared theta minus 1 over sine squared theta is cosecant squared theta. Okay? I know the antiderivative of that. The antiderivative of that is cotangent. Okay? I don't know the antiderivative of this quite yet, though. So let's think about that. Cosine, this is cosine theta over sine theta times 1 over sine theta. That's true, right? I just split up the sine squared into sine times sine. And then that means cosine over sine is cotangent. 1 over sine is cosecant. So this is negative cosecant theta cotangent theta. And I know the antiderivative of that. The antiderivative of negative cosecant theta cotangent theta is cosecant theta. The antiderivative of negative cosecant theta is positive cotangent theta. And that's it. Okay? Definitely takes practice on trig functions inside integrals. It definitely takes practice. The more you do, the easier it gets. All right, number 5. What about this one? What about this one? Well, can't multiply by a conjugate this time. There's not a conjugate involved. We could change tangent to sine over cosine, but then what? I don't know. What do you think? I think we need to just try something. I think we just need to try something. Let's try u sub. Okay? If we let u be tangent x, what would du be? Secant squared. Do we have a secant squared? No. So let's let u be the other thing. If we let u be natural log of cosine x, then what is du? Well, du dx, with respect to x, this would be the derivative of cosine, which is negative sine, over cosine. That's u prime over u, right? Bring over your dx. Do we have this? We sure do. We almost have it. All I need to do is move that negative over. So tangent x dx is equivalent to negative du. So we have here the negative integral of u du, power rule time. So we always get down to something that we can use the power rule on. So this is negative 1/2 u squared plus c. Put back in our x's, so natural log cosine x squared plus c. That's it. Next step, over here. Okay. So I see a rational function, so immediately I look at the degrees and see if I get to divide. The degree at the top here is less than the degree at the bottom, so that blows that. We cannot go and divide. You can only divide if it's an improper rational function. So we can't divide, so you have to think about this. What else can we do? What else can we do? If we let u be the entire denominator, what is du? 2x. 2x. Well, that's interesting, isn't it? Because we have the 2x, we just have that plus 1. Is there anything that we could do to get rid of that? Well, actually, yes, there is something that we can do to get rid of that. We can split up the numerator. I said that you can never split up the denominator, but you can always split up the numerator. This is the same as 2x over x squared plus 1 dx plus 1 over x squared plus 1 dx. You can always split up the numerator. You just can never split up the denominator unless you're using partial fractions, which we will learn in a couple of days. Okay? This, I can use this u sub for. Here exactly is my du, right? It's exactly my du, right there, even with the 2. So this is just du over u. So this would be natural log absolute value of u. And now take a look what we have here. What do we do with that? Well, this is where you have to know your antiderivatives well, because this is exactly arctan of x. This is the most basic arctan. It's just arctan of x. So recognizing is good. This is another one where we don't have to have these absolute values. This would be a safe stop. If it was FRQ, I would totally just stop there. But as a multiple choice question, they would remove those absolute values because x squared plus 1 can never be negative. All right. It would be impossible for me to do examples of everything that we've done so far with integration. So you need to go and practice. Do this very first page. I think the homework is out of the book this time, but do the first homework assignment and it'll give you lots of practice. Do that before you go. We get started on tomorrow's work. Tomorrow we do integration by parts.